כולם פה. אתה רוצה לצפות איתי?
כן, גם בכל מקרה אני לא בטוח שאני יכול לסדר את המחשב למסך.
כן, איך אתה שומע אותי?
כן, משהו...
Okay, good morning, everybody. Please just raise your thumb that you can. I want to be sure that people can hear me. So if you can anybody hear me? Okay, somebody hears me. Good. Thank you. Okay, so let's get started. So I want to start with a question that you asked last time. It was a very interesting question. I don't remember who asked it. So what was the question? So here's a polytope in Rn is the convex hull of a finite thread. So this means the set of all convex. Okay, so that's the definition of a polytope, convex hull of a finite set of points. And the question was, let's say that P, which is a polytope, tiles by translations. If there's a subset of translations, let's call it L0, such that you take the union of all the translates of P by elements of this countable set L0, you get all of Rn and the different translates of P by L have disjoint interiors. We gave an example of this kind of situation where you have a lattice where L0 happens to be a lattice and P is its Voronoi cell, or P is a fundamental parallelepiped or fundamental polytope. Then we get this situation that we're tiling by translations. And the question was, suppose P tiles by translations, does it follow that P lattice tiles by translation i.e. can take L0 to be a lattice. Okay, this was a question that you asked. Let's just do a little example. So example in the plane, take a square, which is the convex hull of 0, E1, E2, E1, E2. This is the polytope. And you can of course tile the plane using this square. This is a little beginning of a picture. So that's a lattice tiling. And so this is a part of a lattice tiling. Maybe I'll add one more layer here. Okay. You can also tile um, with the same square in a non-lattice fashion. So I'm going to offset the second layer from the first layer by some kind of a random amount. Maybe not offset the second layer. The third layer, I mean, maybe offset this layer by another random amount, and so on. So I can definitely use the square to tile space as part of a non-lattice tiling. So this is part of a tiling, which is not a lattice tiling. And suppose some polytope does tile via a lattice tiling. You necessarily also, sorry, suppose some polytope tiles, you necessarily have a lattice tiling? And the answer to this question is yes. And this was proved independently by Venkov in 54 and McMullen, Peter McMullen in 1980. I write the first name down because there's another McMullen that might come up later. So there are two McMullens involved in this theory of geometry of numbers. The proofs are independent. I don't think McMullen knew about Venkov's proof. I put a link to the paper of McMullen if you want to see the proof on the course homepage. And a question that was left unsolved in this paper, and sort of is the main question in this field, is the so-called Voronoi conjecture. So Voronoi conjecture. If P is a polytope which tiles Rn, and hence lattice tiles Rn by result I just mentioned, does it follow that P is an affine image of the Voronoi cell? Was there a question? So, in other words, is there a lattice L and a matrix A in GLNR, F0 in Rn, such that P equals A P0 plus F0, where P0 is the Voronoi cell of L. And let me remind you what a Voronoi cell is. P0 is the set of all X in Rn, the set of points which are closer to the origin than to any other point in the lattice. Okay, so this is still a wide open conjecture, and it's got an interesting history. So first of all, this name Voronoi you're going to hear quite often. So in the Wikipedia page, I found some interesting fun facts about Voronoi and fun facts about some of the other people. So Voronoi lived from 1868 to 1908, and he basically started the field of geometry of numbers in Russia. It founded a very big school in Russia for geometry of numbers. The conjecture was proved, so this is solved for n equals 2, 3, 4, and 5. And along with the solution, in all cases, a list of all possible types of Voronoi cells was obtained. So what I mean by a type of a Voronoi cell is a polytope is a convex hull of some number of points. So one combinatorial property of it is, of course, the number of points. Then you can think about the number of faces of dimension n-1, the number of faces of dimension n-2, the number of faces in each dimension, and you can think about how they intersect each other. So you can say that two polytopes are combinatorially the same if you can match up their vertices in such a way by any map, not necessarily an affine map, but you can form a one-to-one correspondence of their vertices in such a way that all the faces, which are convex hulls of subsets of the vertices, they all map to the corresponding faces of the other polytope. So that's the notion of a type of Voronoi cell. I showed you a picture of types last time. Let me show it another one. So this is the list of types of 5-dimensional Voronoi cells. So there are 5 of them in 3 dimensions. And so the way that this conjecture has been proved in the dimensions in which it's been proved is actually by listing all these are called parallelohedra. The polytopes that tile bilattices are called parallelohedra. You write down a list of all the possible parallelohedra in that particular dimension, and then you write down a list of all the Delaunay cells, and if you're lucky, it's the same list, and you have a proof of the conjecture. So that's kind of it's a very non-conceptual way of proving a conjecture, but that's the only strategy that's worked so far. And so here's a table. So this
Can I ask a question?
Yeah, sure.
Isn't a fine image of a Voronoi cell necessarily a Voronoi cell, or is there a counterexample?
The affine image, well, what's clearly not, there's a counterexample. If you take a square, then all the affine images are parallelograms. If you make your parallelogram super, super long and thin, it won't be a Delaunay cell for any lattice. It's just too. So basically, Voronoi cells have. That's the answer basically.
Thanks.
But when you take a Voronoi cell for a lattice, and then you apply an affine transformation to the picture, the new cell still tiles, but there's absolutely no reason for it to be the Voronoi cell of the new lattice. Okay, so basically, when you apply affine transformations, the Voronoi cell will change. Okay, so yeah.
A Voronoi cell for a given dimension is uniformly bounded in diameter, or is
The
that
Voronoi cell in a given dimension, I think, is uniformly bounded in diameter. Let me think for a moment. Yeah, I think that's true, although right now I'm blanking on finding a proof. Definitely, I think that's true.
Yeah, okay, that's fine. It's an exercise.
No, sorry, that's not true. That's not true. You can take, no, that's not necessarily the case. But still, these very degenerate, basically in 2 dimensions, these rather degenerate parallelograms are not going to be Voronoi cells. The Voronoi cells in 2 dimensions are either rectangles, so they're parallelograms with right angles, or they're hexagons. So as soon as you perturb your rectangle so that it has angle, it's not a Voronoi cell anymore. Okay, so this is the only, so I said that the only cases known are 2, 3, 4, and 5. And let me just say, write down the number of Voronoi cells, the number of possible types of Voronoi cells in that dimension. So in dimension 2, I just mentioned that there are 2 possible types of Voronoi cell. That's the square and the hexagon. In dimension 3, there are 5. That's the picture that I just showed you. And in dimension 4, there happened to be 52. And this was proved by Delaunay in 29. And sorry. Right. So this was, so the conjecture, I guess what I said is a little bit off. So the conjecture, so this was proved, list was, okay, there are 52, and the list was completed in 73. And the Voronoi conjecture was proved in 29 by Delaunay. So this is a bit of a contradiction to what I said before. I'll get back to this in a second. And in dimension 5, there are about 110,000 Delaunay cells. The list was completed in 2016, and the conjecture was proved. Just the preprint came out this year by 2 people. One of them is Magazinov, so Garber and Magazinov. Some of you may know Magazinov. He was a postdoc at Tel Aviv and working on this while he was here, and he went back to Russia 2 years ago. So what I said was a little bit not accurate. In this case, in dimension 5, what happened was that the first was the list of all parallelohedra. It was first completed, and this was in 2016. And then the list, and then it was verified that this, by Garber and Magazinov, that all of these parallelohedra are actually Voronoi cells. I don't exactly know this history of how how Delaunay was able to prove this in 29 before he had the full list of these Voronoi cells. I thought it was impossible, but I guess that's not true. At least wasn't true
Sorry.
before. Yeah.
I have a question. You said in dimension 2, maybe I'm misunderstanding what's written. In dimension 2, the only Voronoi cells are square in a hexagon?
Yeah, combinatorially speaking. So there's a rectangle. There's all sorts of hexagons. The hexagon is not necessarily the regular hexagon, but combinatorially they either have 4 vertices and they're combinatorially equivalent to a square, or they have 6 vertices and they're combinatorially equivalent to a hexagon.
Okay.
That's
Thanks.
One more thing, you'll be hearing the name Delaunay throughout the course. So Delaunay is also, he published his papers. He's a Russian mathematician. He's a student of Voronoi. Voronoi lived for 40 years, died young. Delaunay lived for over 90 years. He didn't die. He died at the end of near the end of the 20th century. And this is the way he spells his name when he publishes in German, and this is the way he spells his name when he publishes in French. And somehow both spellings have survived. So some people are not, there's some things named after Delaunay coming from papers they wrote in German, and other things coming from papers they wrote in French. And some people are not aware that this is actually the same human being. He's also quite famous in Russia, regardless of mathematics, because he's one of the best-known mountain climbers in Russia. He climbed some of the mountains he was the first to climb some of the mountains in Russia. So that's just a colorful tale about Delaunay. So that's what I had to say, just for fun facts, sort of regarding the question that was asked last time. Any questions about this? Okay. So now let me move on to another topic, which is I want to characterize lattices. So sometimes, so we defined, so let me write down the name of the topic, characterization of lattices. We defined a lattice to be the span over Z of a basis of Rn. Sometimes you're given a subset of Rn, and you want to know whether or not it's a lattice, and you're not given a basis for it. And we're going to see that it's quite a difficult task, actually, given a subset of Rn, even if it is a lattice, to find a basis for it. It might be quite a difficult task. And so you want to have another way of figuring out whether a given subset of Rn is a lattice. So there's a characterization, which is very useful. So definitions. Ln Rn is called an additive subgroup. It's an additive subgroup, so it's a subgroup of Rn for the group structure you get by vector addition, which just boils down to saying this. Okay, so Rn with addition is a group, and a collection which is closed under addition, closed under taking inverses, is a subgroup. So that's the definition of an additive subgroup. Ln Rn is any subset of Rn is called discrete if for any L in L there exists R positive.
How we defined lattice to be span, עכשיו אנחנו מגדירים לטיס כזה.
שיה, יש לך, או שאת שואלת או שאת לא...
סליחה.
Okay. L is called discrete if for any point in L is called discrete if for any point in L there exists an R such that if you intersect the ball of radius R with L, you just get L. Okay, so it's the only point. So in other words, it's the only point in a ball. The size of the ball may depend on the point. So in other words, in terms of topology, the topology on L as a subset of Rn is discrete. Let me just give an example. This is a somewhat confusing notion. The notion of discreteness is somewhat confusing. And actually in the books, some people use a different definition of the notion of discreteness. So let me give an example. According to my definition, if you take this set as a subset of R, this is discrete. Right, because at any point in this collection, so around 1 over n, take R to be, I think, definitely 1 over, let me just say, definitely 1 over 10 n cubed will work. There's probably a much smaller number that will, a much larger number that will work, but this will definitely work. You won't have any other point close to 1 over n by this amount in this collection. In some other textbooks, let me write that. So in some textbooks, in some books or literature, discrete in Rn means contains finitely many points. In any ball. Okay, and that's not the case for this example. In a language I'm using, in our terminology, this is equivalent to being discrete and closed. Okay, both. You can check. So I'm just making that caution so that people are aware that the literature contains different terminology. And what's the what's the relationship between discreteness and being an additive subgroup? in the definition of discreteness, for every L, there's an R such that this happens. In an additive group, R can be taken to be independent of L. If you're using the metric, the standard metric, like the Euclidean metric or any metric that's translation invariant on Rn, then R here can be taken to be independent of L. So let me write that down. That's a useful fact. Proposition. If L is an additive subgroup, then the following are equivalent. There exists R such that for all L now, B L is okay. So it's independent of L, and in fact, the proof will actually show that it's enough to. This is the same as saying that there exists an R such that the origin is isolated by the ball of the size line. Let me give these numbers because we're going to be proving these implications. Okay. So in a group, the idea here is that in a group, every point looks exactly the same as every other point. If you're interested in things which are invariant under group operations, and we'll be taking the metric to be invariant in group addition, and then this will follow. So proof 1 implies 3. This is immediate. This is the definition of discreteness. Discreteness says that at every point you can, at every L, you can do something like this. In particular, you can do it at the point 0. Let's prove 3 implies 2. So we're given this R, which satisfies the property that we want at 0, and we want to find some R which satisfies the property that we want at every point, and we're just going to use the same R. So this R and this R will actually be exactly the same R. And so let L be an element of L, and let L1 in L intersect the ball of radius R around that. And I want to prove to you, I need to prove to you that this L1 has to be little l. So now I'm going to subtract everything. I'm going to subtract little l from everything that you see. And so we get that L1 minus L is in L intersect the ball of radius R around 0. Okay, what I did was I subtract little l from here and from here, and I moved the ball around L to the ball around 0. And since I was in an additive group, this element is in my additive subgroup, and it's also in this ball because the metric is translation invariant. So this implication is true because the metric is translation invariant. And L is a group, an additive subgroup. So this means
Barak?
by yeah.
There is a question in the chat which might need some clarification.
You're going to have to speak up. I can't hear you well.
There's a question in the chat from somebody. I do not really...
It was a response to your comment about uniform diameter bound on Voronoi cell. Not important.
But this I was assuming, right?
Yeah, but
okay,
I don't know if it's true. Maybe that's the question.
Let's.
Okay, so it does not relate to this discussion.
Okay. So now we have that L1 minus L belongs to this intersection, and then by what we assumed, by 3, L1 minus L is 0, so this means that L equals L1, so we have, so this proves 2, right? We prove that the only element in this intersection is just L. And then lastly, 2 implies 1 is immediate because it's a square infinite. Okay, so this proves this proposition about discrete sets, discrete groups. And using this, we can state the following proposition. The following, so let L in Rn be some subset. The following are equivalent. So let me write this way. So L is a lattice if and only if one, L is an additive subgroup. 2, L contains a basis for Rn as a vector space. Three, L is discrete. Okay, so that's the characterization of lattices that I mentioned.
So I think 1 is not sufficient. I mean, isn't the trivial subgroup?
No, I'm saying that all of the following, I guess that wasn't clear. So L is a lattice if and only if all 3 of these things.
Okay.
But let me write that down
sure.
more explicitly.
Okay.
Yeah. If and only if the following 3 holds. The following 3 statements hold. All 3 of them. Okay, proof. Let's assume L is a lattice. And we want to prove 1, 2, and 3. So remember that the definition of a lattice is that it's a Z-span of a linearly independent set. So a Z-span is obviously closed under addition and subtraction, and obviously contains a basis because we assume that it's a Z-span of a basis. So 1 and 2 are immediate. For 3, remember from last time that there's a matrix in GR and R such that L is the image of Zn under this matrix. Zn is discrete. Just use R equal to 1, for example. You don't have any elements around 0 in Zn within distance less than 1 except the origin itself. And A is a bi-Lipschitz map from Rn to Rn. Let me remind you what that means. Is this a constant C bigger than 1 such that for all x1, x2 in Rn, the distance from x1 to x2 after applying A is less than the original distance multiplied by C and bigger than the original distance multiplied by 1 over C. So this is what it means to be bi-Lipschitz. If you use this fact, then you see that a bi-Lipschitz map has to map a discrete set to a discrete set. In other words, you could just take your new R to be the previous R divided by C, or maybe by C squared or something like this, and you'll get the. And so I'll just write that down. Bi-Lipschitz maps, bi-Lipschitz maps, some discrete sets. two discrete sets. So this proves 3. Now I'm going to assume 1, 2, and 3, and want to show that L is the span of some for some basis. Okay, let me show you 1, 2, and 3 again, just so you remember what they are. So what we know about L now is that it's an additive group. It contains a basis for Rn, so there's a subset, a basis for Rn that spans Rn as a vector space, but doesn't necessarily span L over Z. We don't know that it spans L over Z, and we do know that L is discrete. So let's start with this basis of Rn that's contained in L and span something with it. So let by, this is 2, by 2, let's take V1 up to Vn, the basis of Rn contained in L, and let L prime be span over Z of V1 to Vn. So L prime is a lattice, and L prime is contained in L. And if L prime equals L, we're done. And let's take a fundamental domain. So I claim, first of all, that L prime is finite index in L as a group. Okay, so let's take a fundamental domain. A bounded fundamental domain for L prime, for example, a fundamental parallel hyped. Remember, we saw last time, we saw last time that every lattice has a fundamental domain, which is a bounded subset of Rn. Let's take it and let's call it omega. Let x1 up to x, well, for now I don't know it's a finite set, so let's take some set x1, x2, etc. be coset representatives for this quotient contained in omega. Right? I can choose coset representatives for this quotient, and whenever I have some coset representative, I can translate it by an element of L prime to land in omega. So I may as well stay inside omega. Now, so this is a collection of distinct points inside omega, and these distinct points are a distance, a fixed distance apart because of the discreteness. It's not exactly the discreteness, it's part 2 of the proposition about discreteness. The distance between any of these 2 points is bounded below by some number. So for any I not equal to j, the norm of xi minus xj is greater than r for some positive r, which doesn't depend on I and j. And this is by the previous proposition. And the fact that, and the assumption that that L is discrete. Remember, the previous proposition was about groups, not about lattices. So, so this means that the set of coset representatives is finite, where D is the index. You can't have infinitely many coset representatives. So now I'm going to take V, be the shortest. So I'm going to continue by induction on this index. So by induction on B, it suffices to find a lattice L double prime, where L double prime is contains L prime not equal to L prime and contained in L. Right? Why is that sufficient? This is an induction on the index D. If D equals 1, there's nothing to do. That's this case. If D equals 1, L equals L prime, and that means that L is a lattice. If D is bigger than 1, then I'm going to replace this L prime by another lattice. So D is the index of L prime inside L. I'm going to find another lattice, L double prime, that contains L prime properly. So the index of L over L double prime is strictly smaller than D, so that would mean that L prime has to equal L. So that's what I want to do by induction. So let's let V be the shortest non-zero element of these coset representatives. I take the shortest one, and let M be the smallest natural number, so that V prime, which is defined to be N times P, belongs to L prime. So if I take this V, and I multiply it by D, by the index, then D times V has to be an L prime, and maybe there's a smaller M, so that N times V is L prime. That's my definition of N, and this is my definition of V prime. Now I claim, I'll prove the claim at the end, claim V prime can be completed to the basis over Z of L prime, i.e. V prime is primitive. We had a notion of what it means for a vector to be primitive in the previous lecture, and that just means that it can be completed. Let's assume this claim. So if I assume the claim, then let's suppose that V prime, I just want to call it, say V1 prime, and then V2 prime, dot, dot, dot. V1 prime are a basis of N prime. And I'm going to define L double prime to be the Z span of V and V2 prime. So this is V prime. It's an element of L prime. V is not an element of L prime. V is a non-zero coset representative, so it represents a non-trivial coset in the quotient. So V is not an L prime, but it has I can multiply it by something and put myself inside V prime. So that means that L prime which is the Z span of V 1 prime, V 2 prime, dot, is contained properly in L double prime. It's contained in L double prime because if you compare the definition of L double prime and you compare the definition of L prime, you see that all the VI primes appear in both places, and V is a multiple of VI prime. So definitely, well, this is not written properly, so the implication is not. L prime, yeah. So L prime, okay, it was okay. Again, each of these VI primes belong to both L prime and L double prime, and V1 prime definitely belongs to this set because it's a multiple of V. So all of these elements belong here, and so L prime belongs here. So definitely we have an inclusion. L prime is contained in L double prime. And also, we don't have equality because L double prime contains this element V, but V is not an L prime. So we've definitely made L double prime, we definitely found a proper containment of lattices, and that concludes the proof modulo the lemmas, modulo the plane. So now we have to prove this plane that V prime can be computed to a base. So to prove the plane, so let's write down this completes the proof. Modulo the plane. To prove the claim, recall from the previous lecture that V, is it V or V prime? Yeah, V prime is primitive. In other words, a vector in a lattice can be completed to a basis in the lattice if and only if it is not a multiple by an integer which is not plus minus 1 as an element of so this was a statement that I proved at the end of the last lecture. So let's see that this holds. I'll just draw a picture. So picture proving the claim. It's a one-dimensional picture. Here is 0. Here is V. Here, say, is V prime, which is M times V. And suppose by contradiction that NV is K times W, where K is not equal to plus or minus 1. K is an integer. So somewhere here, maybe, maybe here there's a W. Okay, and so V prime is an integer multiple of W, and it's also an integer multiple of V. And now I'm going to take multiples of V. So here I have maybe, there's no scale here, scaling here is bad, but here I have GV, and here I have JV, and here I have so here I have JV and J plus 1V. W itself is not a multiple. W itself can't be a multiple of V, because if W were a multiple of V, you see that W minus JV is shorter than V, and so can't be you can't have what am I saying wrong here? It has to be. That's right.
Isn't it just W is shorter than MV, than V prime, and an element of L?
W is shorter than what?
Than MV, than V prime, if
Right.
and an element of L prime, and thus M would not have been chosen minimum.
So V was chosen shortest possible among the coset representatives. I think that's what I'm trying to. I don't think your argument. Let me just. It's W minus JV is not okay. I'm claiming that W minus JV is not in L prime. Again, W is in L prime. W is in L prime, and yeah, okay. So this is W can't be a multiple. W minus JV is not equal to 0 because M is the smallest integer such that MV is in L prime and W is in L prime. So W minus JV can't be 0, but then W minus JV is shorter than V, and that's a contradiction. To the choice of V. V was the shortest possible element, which is a coset representative. So let me, so that's the end of the proof. Let me still take 2 more minutes just to give an example of how this theorem gets used, and then a proposition gets used, and then we'll go for a break. Question?
Can I ask a question?
Sound is, yeah.
So you said that in the beginning of the proof, you took the vectors in the cosets, x1, x2, and so on, and you said xi minus xj is bounded from below by r. And from this, you concluded that you have finite index. And I sort of missed the argument. Why did you conclude?
So any bounded set in Rn, take any bounded set in Rn, and take any subset of it where any 2 elements are separated by some fixed number, at least some fixed number. That has to be a finite set by compactness. You take the closure of the set. Okay.
The set is bounded. The x's are bounded.
No, omega is bounded. We're doing this in a fundamental domain. Where is this?
Oh, okay.
We're doing this in a bounded fundamental domain. We live in a bounded fundamental domain. Yeah.
That's what I missed. Thanks.
Yeah. Okay, let's do 2 examples. I'm just going to show you 2 lattices, which will show up again, and this proposition just helps us be sure that these are actually lattices. So let's take the set L to be, I want to be in R8. I want all the xi's to be integers, and I want the sum of the xi's to be 0 mod 4. Okay? Some definition. This is called the E8 lattice. It's going to appear again. We're seeing it for the first time. It's an interesting lattice. You'll see why in a moment. But why is it a lattice, first of all? So I'm claiming that this is a lattice. It's a lattice by the proposition. Let me not write it down. We can just think about this for a moment. So by the proposition, what do I have to be sure of? I have to be sure that it, first of all, contains a basis for R8. Well, it contains, I'll write it anyway, 4E1, 4E8. The multiples by 4 of the standard basis elements definitely satisfy this condition here because 4 is 0 mod 4. and it's discrete because it's a subset of z to the 8th. And it's and it's a subgroup. So all the conditions of the previous proposition hold for this particular set. You see, this is now the interest in the proposition is I can now know that this kind of definition gives me a lattice without actually telling you what the basis of the lattice is. And in this example, you'll see that figuring out a basis for the lattice might not be a trivial thing. Okay, the next example is sort of similar. Let's go to 4 dimensions. And let's look at the span over Z of the following 4 vectors: 2e1, 2e2, 2e3, 2e4, and the sum of these 4 vectors. So I've 5 vectors. It's not a priori what is a basis for this object, but I do know it's a lattice. Why is it a lattice? Well, the first 4 elements here are a basis for r to the 4. This is also a subset of z to the 4, so it's also discrete, and it's a group. Okay, so this is another lattice. Okay, both of these lattices will appear, so now you know for sure that these are lattices. Questions before we begin?
Yeah. Is this the Hurwitz quaternions?
No, this is,
No.
I don't think so. I'm not sure. I'm not aware of that name. You'll see why I bring it up now. It's just an interesting lattice. Okay, let's take, yeah, sure.
The first lattice, it's the sphere packing lattice in our.
This lattice became, I'll talk about sphere packings. This lattice became very, very famous recently because Marina Vyazovskaya proved that this gives the optimal sphere packing in dimension 8. This is like a big breakthrough that I'll say something about. Probably not today. Okay, let's
question.
take 10 minutes. Oh yeah, sure, question.
The proof of the proposition is constructive, right? So we can actually use it to find a basis, correct?
We'll talk a lot about finding a basis.
Okay.
I somehow, okay, let's postpone that question. I'll just say kind of a mantra in this field. There's something that you might call theoretically constructive. So theoretically it's constructive, but you have to, if you want to implement it practically, you have to be able to find shortest elements of some discrete set, and that's just not a practical thing in any sense, okay? So,
thank you.
It depends what you mean by constructive. Theoretically it is, but somehow it's not practically constructive. Okay, let's take 10 minutes and then continue. Okay, let's continue here. So I'm going to move on to a theorem called Minkowski's first theorem. So and before stating it, let me remind you of something that we did last time. Minkowski's first theorem is a very, very famous theorem, and it's also very easy to prove, actually. And let's remind you of something that we did last time. Recall, we proved in the previous lecture that any two fundamental domains for L have the same volume. Let me remind you what a fundamental domain is. It's a Borel set and a collection of equivalence class representatives for the relation x1 is in the relation with x2 if and only if x1 minus x2 is some element of the lattice. So a fundamental domain intersects every equivalence class exactly once, and it's a Borel set. That's the definition of a fundamental domain. And how did we prove? I'm reminding you of how we proved this result. What we did was, so idea of proof. If this is, say, omega 1, and this is, say, omega 2, then any element here, maybe x2, there's for any element in omega 2, there's a corresponding element of x1 in the same class. So that means that x2 minus x1, or in this notation, x1 minus x2, is an element of the lattice for some L. And what I'm going to do now is partition omega 2 into subsets according to the value of this L. There are countably many possible L's, so there are countably many pieces in this partition. So I'm going to just draw a little bit of color. So maybe all of the elements in this particular pinkish color are related to this particular L. So for every, so A, what we called AL was all the x2 and omega 2, such that x1 minus x2 is equal to L. For every, this is well defined because for every x2, there's a unique x1 here, and then the difference is well defined. It's a well-defined function of x2. And so that's our definition of AL, and then we saw that, and then BL is AL plus or minus plus L. And so that's some subset over here, maybe. And they obviously have the same volume, and omega 2 is partitioned into the ALs, omega 1 is partitioned into the BLs, and so the two sets have the same measure. So that was the proof. This same proof gives a little bit more, so let me write that down as a separate proposition. Suppose you have, let omega, so L is a lattice. And let omega be a Borel set intersecting every equivalence class at most points. Then there's a fundamental domain containing omega, and therefore the volume of omega is less than the co-volume, less or equal to the co-volume of L. Okay, this proposition, let me add, this is sometimes called Lichtman's lemma proposition. In this simple fact. Okay, so another way to say this in the contrapositive is if omega is a measurable set and its volume is bigger than the co-volume, then there have to be two different points in omega that are equivalent. I'll write that down even though it's trivial. Equivalently, if omega is Borel and its volume is bigger than the co-volume of L, then there exists x1, x2 in omega, and L in L not zero, such that x1 minus x2. Okay. Let's prove the proposition. It's basically the same proof. So for each, so fix a fundamental domain omega 1 for L. For each L in L, define AL to be exactly as I defined before for omega 2. I'm just making the same definition for omega, which I don't know is a fundamental domain. I just know that it intersects every equivalence class at most once. So this is the definition. And since it intersects, since each equivalence class intersects omega in most ones, if such an x1 exists, it is unique. And so for L1 not equal to L2, AL1 and AL2 are disjoint. And now the volume of, now let me just write down that omega prime, which is omega union the complement is a fundamental domain containing omega prime. All the equivalence classes that are already represented by elements of omega, I just keep them. And if there are classes which I've missed, then they are represented by some element of omega 1, and they're not equivalent to anything already represented by omega prime. In other words, this set here is the set of elements of omega 1, which are representing the same classes represented by elements of omega. I don't want to use them again, so I throw them out, and what's left over is representatives for all the other classes. So that's the proof of the lemma. You notice that all the operations that I'm doing, namely taking sets and translating them, or taking these countable unions, push Borel sets to Borel sets. And so that's why it's very useful to work with fundamental domains being allowed to be Borel sets rather than nicer sets like parallelohedra or something like that. Okay, questions about the lemma? Okay, so now let's state, or let's definitions before stating the theorem. So I already defined what it means for a set to be convex. K, let K and Rn be convex. K is called centrally symmetric. I mentioned this last time. If K equals minus K. So in other words, whenever an element of minus K by definition, minus K by definition is just the minuses of elements of K. So whenever an element is contained in K, then so is minus of that same element. So in other words, the set is symmetric around the origin with respect to this inversion. And the Minkowski's first theorem says the following. Suppose K is convex and centrally symmetric. L is a lattice. And the volume of K is bigger than 2 to the n times the covolume of L. Then K intersect L is not equal to 0, or let me just E. K contains an element of L minus 0, a non-zero lattice. So every centrally, okay, let's just look at this for a few seconds. Every centrally symmetric convex body contains 0. Why does it contain 0? Because if it's non-empty, of course. So if it contains one point, it contains minus that point. That's just central symmetry. Then by convexity, it contains 0. Lattices also contain 0. And so this intersection over here always contains 0 when K is centrally symmetric and L is a lattice. And we're interested in whether K contains an additional point. In other words, a non-zero element of the lattice. And the theorem says that this is going to happen whenever the volume of K is bigger than this right-hand amount, 2 to the n times the covolume of L. Okay, so notice that this condition sort of is reasonable because it's invariant under, you can take, there's a natural operation you can do to convex bodies and also to lattices, which is just to uniformly expand or dilate the whole picture by a constant. So if you do that to L, the covolume grows. If you enlarge L by a factor of, say, T, the covolume grows by T to the n, and the same happens to the volume. So sort of this formula is invariant under dilations. Okay, proof of the theorem. It's almost an immediate consequence of the Dichter lemma. So let's let K0 be 1/2 k. So in other words, you take all elements of k and you take the point halfway to the origin. And so we're contracting k by a factor of 1/2. So if you figure out the Jacobian of this mapping, then you see that the volume of k0 is 1/2 to the n, that's the Jacobian, times the volume of k. And by assumption about the volume of k, that's bigger than the co-volume of L. And the co-volume of L is the volume of omega, where omega is a fundamental domain. Well, just by definition. And so if you use the Blichfeld lemma in the contrapositive, where did this go? Equivalently, if we use this formulation, whenever we have a set whose volume is, sorry, this one, volume is bigger than co-volume, but here don't use omega, use k0. Whenever this happens, then there are 2 points in this set whose difference is a non-zero lattice element. So by the Blichfeld lemma, there are x1, x2, and k0 such that x1 minus x2 is an element of L, and it's not zero. Xi is in k0, which is 1/2 of k, so I can write xi as 1/2 of yi for yi in k. And then I get that x1 minus x2 is 1/2 y1 minus 1/2 y2, which is 1/2 y1 plus 1/2 negative y2. Y1 is an element of k, y2 is an element of k, and k is centrally symmetric, so minus y2 is also an element of k. This is a convex combination of 2 elements of k. K is convex, so we're in k. So x1 minus x2 is a non-zero element of L intersected by k. And that's the proof of the Minkowski's theorem. Okay, questions about the proof? So this theorem is sort of very famous in geometry of numbers, and it has many, many applications. We're going to see one way of thinking about it today, but it's going to show up again during the course several times. There are many, many questions that this theorem raises. Let's just say one thing about it. The only thing I want to say generally about this is that, where did this go? The condition is tight. So in other words, if it's almost tight. So in other words, it's exactly tight. So if you look at this condition, you might ask, can we change this constant? And I'm claiming that you can't change the constant, and the standard example here is the integer lattice and a cube. And you take the cube to be an open cube. Let's write that down. So example, so an open L infinity ball. So if L is z to the n and k is minus 1, 1 to the n, so this is the open L infinity ball, then the volume of k is exactly 2 to the n. The whole volume of L is 1. And so the theorem is sharp in the sense that 2 to the n can't be reduced. Okay, but we're going to be seeing many other questions related to this. For example, you could ask, this theorem guarantees that there's one point. If the volume is, you can think about it this way, if the volume of the set K is large enough, it contains at least one element of the lattice. Well, maybe it contains more. Maybe if the volume becomes much larger, then the number of elements also becomes larger. And then how does that work? And indeed, that's a well-studied direction. And maybe we saw that it's sharp for the cube. Maybe it's not sharp for some other centrally symmetric convex bodies, like the Euclidean ball. And we'll see that it's actually not sharp for other bodies. And so there are many, many questions that this.
Can we allow equality if we take K to be closed or compact?
Yes, thank you very much. It's an exercise actually that I'll put on your exercise sheet. Exercise, it's not very hard. If K is also assumed to be compact and you have equality, well, let me, since you've asked, it's kind of annoying if someone says you're right and you can think about that yourself. So let me just say it as a proposition. If K is compact and the volume of K is equal to 2 to the n for volume of L, then K contains non-zero point of L. Proof for each epsilon, or let's say each n, n is taken for each j, integer j, by Minkowski's theorem, there is Lj non-zero in L intersect 1 plus 1 over j times k. Okay? So what I'm doing is I'm taking k and I'm inflating it by a factor of 1 plus 1 over j. That has the effect, this is a new symmetric convex body. K was symmetric, so this is symmetric, K was convex. So this is convex. And now for this new body, we have strict inequality here. So we can apply the Minkowski theorem and find a non-zero element here. Okay? And past all of these guys, this is a sequence that lives in a bounded set. So Lj is a bounded sequence. Because it's contained in, for example, 2 times K, and has a convergent subsequence. Lji converges to some L0. By discreteness, Lji is in L, so a limit of elements of L has to lie in L. L is closed, but it's also not zero because the discreteness of L says that all of these points here are not close to the origin by some definite amount. So this converges to some non-zero point of L, and Lji is in 1 plus 1 over ji kj, and so the limit point, let's call the limit point, yeah, so L0 is in the intersection of these things. And you can check that that's equal to K, and this comes from the compactness. Okay, so that's the answer to your question, which was supposed to be an exercise. So
thank you.
You get 2 points from your fellow students for saving you the trouble of having to think about this. So this is okay. This is about the Minkowski's first theorem. Now let's use this to talk about something called Minkowski successive minima. So that's our next topic. And here we're moving to away from the algebra of lattices, and we're going to see for the first time the kinds of things that we mean when we talk about the geometric characteristics of lattices. So far, all lattices are more or less the same. Algebraically, they're all more or less the same. But now we're going to start seeing differences between different lattices. And so there's this notion of the successive minima of a lattice. So L is a lattice. For I between 1 and n, we can define lambda I of L to be the inf over the positive R, so that L intersect the ball radius R contains I linearly independent vectors. Okay, let's draw a picture. So before I do that, let's just say this ball for the moment is the Euclidean ball. This is L2 ball. We'll discuss more general norms and convex bodies in a second, but this is the first definition. And so let's do a picture. So here is 0, and maybe the lattice looks like this. Okay. Let me use my all right, so when R is small, so this is R1, say, this radius is R1. When R is small, all the lattice elements in this ball are just 0. So there's no, the dimension of the space spanned by this is 0. Now, when I increase R and make it larger, this is going to be R2, I pick up some vectors, namely I pick up these non-zero vectors. And so now the dimension, now the set, the ball of radius R2 intersect the lattice consists of these 3 vectors. And so it contains one linearly independent vector, but not 2, because any 2 here are linearly dependent. They're on the same line. And when I make this even longer, I pick up 2 linearly independent vectors, namely, say, this one and this one. Okay? And so the definition is, I'm interested in the smallest, the infimum of the R's, so that I get at least I linearly independent vectors. And so lambda 1 here would be this distance to, let me draw that in red. This distance would be lambda 1. If I'm smaller than lambda 1, I don't have any vectors, non-zero vectors inside. If I'm bigger than lambda 1, I start seeing this particular vector over here. And so the infimum of those for which I have a non-zero vector are these. So lambda 1 is the, let me write that down. Lambda 1 of L is the shortest. Lambda 1 of L is the shortest non-zero vector of L. And in this example, lambda 2 is going to be this distance here. It's going to be the next shortest vector, which is linearly independent of the first vector. So when I increase the ball so that it's bigger than this distance, from the distance to this vector, I start seeing this vector inside and also this vector inside, so the dimension becomes 2. And before that, the dimension is 1. So that's this definition here. Now you could work with closed balls. Let me write that down. You could work with closed balls as well as open balls. So, erase this for a moment. All right. So all I've done here is replaced the open ball by a closed ball, closed O2 ball. And the advantage of working with closed balls is that in a closed ball, this set is always finite. Well, it's also always finite in this situation. But if you're working with closed balls and you do something analogous to the proof that I just gave in response to the question, you'll see that this infimum is actually a minimum. It's actually achieved because of the compactness of these balls. And so I'll just write that down as an exercise for you, which is basically what I did in the previous argument. So this is an exercise that the infimum are the same if I work with closed balls. Okay, wonderful fact. And we can ask ourselves question, given L, what are the values of this geometric characteristic of the lattice? And a related question, which I'm going to add to this, is what is a good basis for L? We already know that the same lattice can have many different bases. So you might ask yourself, well, what's geometrically a reasonably good basis for L? And what I mean by that is somehow it's economical to use if you're doing computations with this lattice. So in this particular picture that I drew over here, it sort of seems clear that this first vector and the second vector, they form a good basis, and they also realize lambda 1 and lambda 2. Their lengths realize lambda 1 and lambda 2. It's kind of, it seems rather silly to take a continuous lattice along. It also has another basis which consists maybe of this vector and, well, no, it consists maybe of, sorry, this vector and this vector, v1, v2. That's also a basis for the same lattice. And it's sort of clear from the drawing that it doesn't really make sense intuitively to use this particular basis. They're just too big and they don't tell you anything geometric about the lattice, where these two are actually better. So somehow figuring out the success, these numbers are called the successive minima. Figuring out the successive minima is quite closely related to the problem of choosing a good basis for the vector. So let me show you something, an example that's somewhat confusing when you see it at first. And so exercise, which you're going to do in your exercise sheet, there is a sequence of vectors. Well, let's just call it a basis for Rn. Contained in L, such that the norm of lambda I is Vi. So in other words, you can always choose n elements of your lattice which form a basis for Rn, but note that this is a basis as a real vector space and not a basis as a lattice. Okay, and they are realizing these successive minima. In this example, that would be again these two vectors here. This vector would be the first one, and this vector would be the second one. And the proof, well, you're going to prove it yourself, but the idea of the proof is some kind of greedy algorithm. Take the shortest vector. Just take the short v1 up to vi, choose vi plus 1 to be the shortest, so that v1, vi plus 1 are linearly independent. So this is what I mean by a greedy algorithm. In this greedy algorithm, there may be ties. So in some cases, it may be the case that there are two vectors of the same length at some point. Well, then you just choose one of them in some way, some tie-breaking mechanism. So you're going to prove in your in the exercise, it's not hard at all. You're going to show that in this way, you obviously are choosing a basis for Rn, and you're going to show that this basis realizes the successive minima. Let me show you an example. This seems very intuitive, and many algorithms are based on this idea. But let me give you an example showing that the situation is not as clear as you might think. So, example. Let's take L to be the span of, well, I had this, sorry. We were using this lattice earlier. Let's do two lattices, 2E1, 2E2, 2E3, 2E4, E1 plus E2 plus E3 plus E4. Span over Z. I'm defining two lattices, one in dimension 4 and one in dimension 5, and defining them by the same way that we saw earlier. So this L1 we already showed quickly in an example. L2 is sort of the same idea and one dimension higher. And let's sort of run the, you notice that in both cases, we know these are lattices from the previous proposition because they're discrete groups, etc. But we don't have a basis at hand, because in this collection, there's one vector too many. So let's figure out the lengths of these vectors and think about the previous algorithm. So the length of this guy is 2, the length of this guy is 2, the length of this guy is 2, the length of this guy is 2. Here we have, by Pythagorean theorem, the square root of 1 plus 1 plus 1 plus 1. So the length of this guy is also 2. Okay? So all the 5 vectors have the same length. Now, I said a second ago in this idea that there may be ties, and when there are ties, you break the tie in some random way. So what you could imagine doing is you first choose the shortest vector here. Well, there's a tie, so let's just choose this one. And now you want to choose the second shortest. Well, again, it's one of these guys. There's a tie, you're supposed to choose this one. If you choose these 4 elements first, they don't generate this, they don't span this guy, so they're not a Z basis. So note that in L1, the span over Z, 2E1, 2E2, 2E3, 2E4 is a proper sublattice. L1 does not contain E1 plus E4. So the greedy algorithm just mentioned doesn't necessarily give a basis. It this?
A question?
Yeah.
Formally, you should show that there is no vectors of shortest length span, right? Yeah.
Right. We're gonna say, yeah. We're gonna show that now. Actually, good point. I forgot to do that. So, yeah. So note. So this should have been earlier here. Note that there are no shorter vectors. So if you, in L1, if you think about this lattice here, and you think about the entries mod 2, and you think about the entries, so this guy has all, this first vector has all its entries even. This vector has all its entries even. This vector has all its entries even. This one too. This one has all its entries odd, right? So any vector in L1 either has all xi even or all xi odd, right? If it has all xi's odd, then its length, the length is greater than or equal to square root of, right? An odd number, an odd integer is at least 1. So you have 4 entries. Each of them has size at least 1 in absolute value. And so the length is at least 2. And if all the xi's are even and v is not 0, then the length is again bigger than 2 because one of the entries is at least 2. Okay? So these are the shortest vectors. Thank you for the comment. And if we pass to the lattice, you could say, well, okay, you were just being silly. You shouldn't, when you were doing the tie break mechanism, in other words, when I saw that this vector was equal to the other vectors in length, I should have been more careful about which vector to choose. You might say that that's why this sort of thing came up. Well, that's not the case because this example shows that these first 5 vectors are the shortest. This 6th vector is strictly longer, right? Their length is 2. This length is square root of 5, which is bigger than 2. So if you choose these 5 vectors, you won't get this vector in the z-span of the basis you're choosing. Okay, so choosing a basis for a lattice is not a completely trivial thing. Let me, before the break, let me just do one more example to sort of explain. This is more of a story than 2 more interesting examples. I'm not saying much about them, but we'll see these guys later, these lattices later. The E8 lattice that I defined before, I have to recall, I prepared this, but I don't remember this by heart. You could ask how many shortest vectors does it have? Has 240 vectors which realize lambda 1, so they're the shortest. This is in 8 dimensions. Note that Z8 has 16, so plus minus the elements of the standard basis vector. So you have lots of vectors to choose from. So if you have ties, you can imagine that figuring out how to break the tie in a reasonable way is not at all clear if you have that many elements in your tie. Just to sort of give you a kind of a stronger sense that this is an interesting lattice, let me just say that the Voronoi cell in this case has 17,280 seven-dimensional faces. So what this means, remember, what is the Voronoi cell? The Voronoi cell is what you get if you look at the closest, every point is in a Voronoi cell if it's closer to the origin than to any other point of the lattice. So these are all the points that are quite close to the origin. But saying that it has a face, a seven-dimensional face, or a codimension one face, means that when you're on a face, it means that there's a tie between two vectors. So two vectors, you're closest to zero, but you're also closest to some other non-zero vector. Otherwise, you'd be in the interior. So basically what that means is for vectors which are close to zero, if you want to know whether you're closest to zero than to any other potential nearby neighbor, you have to compare yourself to 17,000 other vectors. That's a huge number. So there's lots and lots of possible close ties. Okay, there's a famous lattice in 24 dimensions, the Leech lattice. This is a famous lattice in 24 dimensions. Has similar properties. It has lambda 1. So there's lots and lots of vectors realizing the shortest vector problem. And this is realized by 196,560 vectors. So lots and lots and lots of vectors. Voronoi cell has 16 million and some number faces. So what these examples are supposed to show, this is all on a very intuitive level. What these examples are supposed to show you is that, and this is related to the question that we had in the previous hour about whether a certain algorithm is constructive. So the algorithm sort of makes theoretical sense, but if you're faced with a practical problem of choosing the shortest vector and you have this number of competitors that you have to look at, or maybe this number of competitors that you have to look at, even if the dimension is not too large, the dimension here is 24, you know that there's, that this is practically, it might be a complicated problem. And these lattices are very famous. We're going to discuss these two lattices in more detail later. But you might tell me, well, okay, of course, you came up with these weird examples that are very weird and very pathological, and they have a lot of short vectors. But maybe typical lattices are closer to Z8, when the number of short vectors is sort of small. Or maybe they're even better. Maybe they're closer to the example that I drew here, where it's sort of obvious when you look at the picture what the shortest vector is. Well, the answer is no. The answer is that most lattices, in many technical senses, most lattices sort of look like the Leech lattice or the E8 lattice in the sense that they have lots and lots of competitors for being the shortest vectors. There's lots and lots of vectors of almost the same length. And lambda 1 and lambda 2 and lambda 3 up to lambda n are typically very, very close to each other. So this is sort of you can imagine just taking the Leech lattice and perturbing it just by a linear transformation with a very small linear transformation. Then maybe we have inequality. Maybe lambda 1 is a bit smaller than lambda 2, lambda 2 smaller than lambda 3, all the way up to 24. All these 24 numbers are distinct, but in order to find them, you have to search among a huge number of competitors to figure out which one is the shortest. So that's kind of a typical picture for a generic lattice, and that's something we're going to discuss. Okay. Questions about this definition? Okay, so let's take a 10-minute break and talk more about successive minima.
Excuse me, can I ask a question about?
Sure.
So before we looked at the lattice, which was spanned by 2e1, 2e2, 2e5, and the sum of them. Isn't that a counterexample where we have a basis that the size of the ith vector is lambda I? I mean, because like all the lambda i's are 2, and so we have to take 2e1, 2e2, 2e3 to 2e5.
Say, no, the proposition didn't say that there's a basis of the lattice that has lambda i's equal to the norm of vi. That's not true. I said that there's a basis of Rn where the lambda is.
Okay, a basis of Rn in the lattice.
Yes.
Okay, right.
That's exactly the point. You can't, this greedy algorithm finds a basis of Rn inside the lattice with realizing the lambda i's, but it's not a basis of the lattice.
Okay.
In the sense of basis of lattice.
But like the correct algorithm must be some sort of like a modified greedy algorithm, right? Because like in the end of the day, those.
Okay, you're exactly anticipating what I'm going to say now. So let me say it, and then you can ask if it's not clear. Okay, so what's being proposed here, is the following, so kind of proposal for a revised greedy algorithm. Again, before I continue, the issue now, the difficulty now, is that we don't have a smart way to choose a basis for the lattice in the sense of bases of lattices, so a generating set over Z of linearly independent vectors, which realizes these successive minima. And in fact, the previous example shows that this doesn't have to exist. But we could still sort of try to describe some kind of an algorithm that chooses something you might call the most economical basis, whatever that really means. So here's a proposal for some kind of a greedy algorithm, but I'm not going to be too precise about it, but you'll see that it's going to run into problems, and this is something that we're going to discuss. So you could say, well, choose V1 to be the shortest vector in L, so the norm of V1 is lambda 1. Now you might say choose V2 to be shortest among V2 so that V1, V2 is primitive. So in other words, not only do I want to require that V1 and V2 are linearly independent, I also want to require that I can complete them to a basis. We saw in the previous lecture last week that for the first vector to be primitive, in other words, for this vector to be completable to a basis of the lattice, it's enough to assume that it's the shortest non-zero vector. I'll remind you what the general, what we saw last week. Last week we saw V1 up to V, say, K is a primitive K tuple, meaning it can be completed to a basis of the lattice if and only if the span over Z of V1 up to Vk is equal to L intersect the span over R of V1 up to Vk, and Vi are linearly independent. Okay, those are the two conditions. And so clearly if K is 1 and it's shortest, then, okay, if you look at this formula, the left-hand side is always contained in the right-hand side. That's clear. The question is it true that the right-hand side is contained in the left-hand side? So the shortest vector in a one-dimensional case has this property. The multiples of it that enter into L, since it's shortest, can't be multiples of it by scalars less than 1. And so that means that this is a subset of this. But in the general case, so that means that the shortest vector is already primitive. And the suggestion here, or maybe that's not your suggestion, but I'm sort of taking this as a suggestion, you could sort of say, let's just take the shortest among the V2 for which V1 and V2 together satisfy this condition. And then you can continue. So successively, given V1 up to Vi primitive, choose Vi plus 1 short as possible so that V1 up to Vi plus 1 is also primitive. That's something you might try to do. And then you might ask yourself, well, is this a good algorithm? Well, definitely this is going to give you a basis of the lattice just by construction. And you could ask, is this a good algorithm? For example, you could ask, well, suppose I didn't use a greedy algorithm, and suppose I wanted to take the primitive, the basis for which the last vector chosen, the longest vector in the basis, is as short as possible. So that would sort of put me as close as possible to lambda n. Maybe that's my notion of being a good choice. Well, there's absolutely no guarantee that this algorithm will solve that problem. Or you might want to say, well, I want to minimize the sum of the differences between the norm of V1 and lambda 1, the norm of V2 and lambda 2, etc. Whenever I have a big gap, I pay a penalty. Is this algorithm a good algorithm? No guarantee whatsoever. All of these problems are just difficult, and there's no easy solution to them. And so we need to come up with some kind of a notion for what it means to choose a economical basis or a good basis. Are any questions about this? Was this the more or less the kind of question you wanted to ask? Okay, so if no questions, I'll just continue. So that's just a kind of informal discussion. It's sort of hard to formalize what we mean when we say we want the most economical basis of our lattice possible. And even if we do formalize it, it's hard to come up with a procedure that does what we want. So there's a famous algorithm for choosing a basis. This is called the Corkin-Zolotard reduction. Corkin-Zolotard reduction. This is an algorithm from 1873. Algorithm in the sense you can't implement it because it involves choosing the shortest vector in a discrete set, which is a very difficult problem, but it's a theoretical algorithm, and it's going to find you a basis at least for the lattice, and this is what you do. So this is so given a lattice L gives a basis for L, and I'll write in brackets something which is not precise. It's an economical basis in some sense. You don't choose terribly long vectors, but I'm not making this notion of being economical precise. Okay, so here's what you do. So first, let V1 be the shortest non-zero vector. Now, successively, suppose we've chosen V1 up to Vi. Let's let V be the stem of the V1 up to Vi. So this is some I-dimensional subspace of Rn. And let's let pi from Rn to V be the orthogonal projection. Then, so then I look at let U I plus 1 be the shortest non-zero vector in the projection of L. So we will see that this, we will see soon that pi of L is discrete. Okay, so pi of L is some subset, some discrete subset, some lattice actually in V, in this I-dimensional subspace. And ui plus 1 is the shortest vector in pi L. And take vi plus 1 to be the shortest vector. The shortest vector that projects onto ui plus 1 under this orthogonal projection. And that's your algorithm, and that chooses for you the VIs one after another. And the proposition here is that, first of all, this is well defined. Well defined means I'm not claiming there could be ties. Even in the first step, there could be ties. There could be several V1s that represent, that are simultaneously the shortest vector. And then you have to choose one. I mean, if you make different choices, then you'll be choosing different bases. But what I mean by well-defined is that here, I said that pi of L is discrete. If pi L was not discrete, there needn't be a shortest vector in pi of L, shortest non-zero vector. So this is well-defined means that at each step, pi of L is discrete, and the V1s here up to the end are a basis for over Z. That's what Korkin and Zoltan proved. Proved by induction that V1, Vi are a primitive.
Sorry, the question about the definition there.
Question on what?
Don't we need to choose at each step when we choose Vi plus 1? Don't we need to like make sure that it's not, we also
Make sure that it's
need
not
to
what?
choose it to be the shortest one that's not already in the span of the Vi?
It's not going to be in the span of the VIs because it's projecting to ui plus 1. You see, this means it's projecting to ui plus 1, and ui plus 1 is not 0. And the only things that are in the span of V1 up to Vi project to 0 under this orthogonal projection.
Oh, I see it. Okay.
That's going to show up in the proof. So we're going to prove by induction that V1 up to V. Yeah, sure.
Can I expand on that question? So do you project onto V or onto V perp? I'm kind of
projecting onto V and choosing.
So what happens if like V1 is still the shortest amongst all the projections there? Then you just choose V1 and you're stuck with it. I think that's what.
Oh, I'm sorry. I'm projecting onto the perp. Thank you.
Okay.
Perp.
Thanks.
Yeah, I guess that was the same question. So is everything else correct? Yeah, there's projection onto the perp. Thank you. I think the previous question was basically asking the same thing. Okay, so we're going to prove that by induction on I that V1 up to Vi are a primitive I couple for each I. Let's go back to this. Recall this characterization of what it means for a k-tuple to be primitive. So we're going to check things by using this characterization. And I already said that when you choose V1 to be the shortest, this holds. So that's the basis of the induction. So V1 is a primitive I tuple, a primitive 1 tuple, because it satisfies this condition. So let's give this condition a name here. let's call this statement A. There was a corollary something last week, corollary 4, corollary 5. Let's just call it A for now. So V1 is primitive by this statement A. Suppose V1 up to Vi already chosen, and so they are primitive by induction. And since they're primitive, I can complete them to a basis and I'm calling the vectors that are needed to complete them W1 up to Wi plus 1 up to Wn. Okay? This is what it means to be primitive. So such a basis exists. Okay, now let's look at pi of L. So pi of L is the Z span notation span over Z of pi of V1, pi of Vi, pi of W1, pi plus 1, pi of N. But all of these guys here are 0 because we're projected onto the perp. And so this is the Z span of and these are n plus 1, these are, sorry, n minus I linearly independent vectors, n minus I linearly independent vectors in V, where V is a vector space of dimension n minus 1. If there were any linear relation, among these Wi's after projection, then there would have been a linear relation in this collection before the projection. And so these guys are linearly dependent in V, so actually they form a lattice in V, so they're discrete. So that's just, so pi of, so this is, so pi of L is discrete. Okay? And so now the algorithm is well defined, and we're going to verify A for the collection that you get by adding Vi plus 1. In order to do that, what we need to do is we need to take a vector which is in the lattice, and it's also in the R span of these vectors, and prove that it's in the Z span of these vectors. So let's call it W in L intersect the span over R, V1, Vi plus 1. Let's first look at the projection of W. If pi of W equals 0, then W was actually in the span over R of V1 up to Vi. And since the VI's and by primitivity of V1 up to Vi, W was in the Z span of V1 up to Vi. So suppose it's not 0. If pi W is not 0, then pi W is in the span of pi of Vi plus 1. Right? Because all the other span over R, because all the other, W is here. I'm sorry, W is here. But all of these guys project to 0. So it's actually, when you project it, it's a multiple of this guy. But what is VI plus 1? VI plus 1 is the shortest representative of something projecting onto UI plus 1, where UI plus 1 is the shortest element here. So this is a span of, so this means that the pi of W is a multiple of pi of VI plus 1, which is UI plus 1. And UI plus 1 is the shortest element in pi of L, non-zero element. So pi of W is K UI plus 1 for some K. And now we look at the difference. W minus K UI plus, sorry, W minus K VI plus 1 pi satisfies that pi of W prime is 0. And so W prime is in the span over Z of V1 up to VI. And so W is in the span over Z of V1 VI plus 1, which is what we needed to put. Okay, so this proves this Korkin-Zolotayev statement. This Korkin-Zolotayev lemma. So this is basically, even though it's from 1873, it's sort of the only reasonable algorithm that I'm aware of choosing a basis for a lattice which is sort of reasonably economical. There's really no other algorithm, and you're going to see that this is not a terribly successful algorithm if you really want to know that you've chosen the most economical basis possible in whatever sense of the word economical you want to use.
So, can I ask you a question? You said that this algorithm cannot be implemented in the beginning. I didn't understand what you mean. You said something, you relativized the statement that it's an algorithm in the sense that it cannot be implemented.
Right. So all of these issues are apparent in what I showed at the end of the last before our break when I discussed the E8 lattice and the Leach lattice. What you should be aware of is that many lattices, if you're asking for the shortest vector, you're going to find a huge number of candidates. And when you try to run this kind of thing on a computer, either that will mean that the computer has, that it's an exponential problem in the input somehow, or it might mean that it's very, very susceptible to small computation errors like round-off errors and things like this. So all of these ideas where I say something like, choose the shortest in the following collection, even if you know that there is a shortest thing, the collection that you're looking at is typically a lattice, say in 20 or 30 dimensions, and just choosing the shortest element there is not a feasible task.
Okay, and so it's extremely impractical in some sense.
It's extremely impractical.
It can be formulated, but it just will not work. That's
exactly.
What you. Okay.
And that's we're going to discuss computer science connections later, but that's not a bad news. So I guess Apple is very famous when some of the Apple machines came out and there were problems with them. They would say, well, that's not a bug, that's a feature. So for us, this is in some senses, it's a useful thing that this shortest vector problem can't be solved in a practical way, because that's the basis of a lot of interest in computer science and in cryptography, in these kinds of, in lattice questions. We're going to discuss a little bit about lattices and cryptography later in the course. But the picture you should have in mind right now is that whenever I say shortest lattice vector or shortest vector in some discrete subgroup, additive subgroup, that's not a feasible thing to actually implement in high dimensions. Okay, what I want to do next is, so we have 20 minutes. I'm going to state a theorem and discuss the theorem, but the proof will be postponed until next time, and this is Minkowski's second theorem. So that's our next topic. It gives a relationship between these lambda i's. Let me first state it so you know what it is, but then I will give more details and remarks. So for any lattice L and any lattice L, sorry, you look at the product of the look at the product of the n successive minima, and what you get is bounded above and below by constants depending on the co-volume of L. Okay, and this is a special case, and we're now going to. I'm going to move to the general case now, just to state the general case. So, okay, but as a kind of a first approximation, what you should have in mind is the following picture. So imagine that you're only interested in lattices where the co-volume is fixed. Okay, and imagine that we're interested in all lattices and in a given dimension. We're not changing the dimension, and we don't care about constants. Okay. So then if that's what you care about, you can ignore this constant. And so what you're seeing is that the product of these lambda i's is approximately 1. In other words, if you make lambda, and obviously from our definition, lambda 1 is bounded below by lambda 1 is smaller than lambda 2, etc. up to lambda n. And so what that means essentially is that if you have a lattice for which lambda 1 is very small, it must be the case that lambda n is very large. Okay, because their product has to be approximately 1. Again, I'm talking about covolume 1 lattices. Okay, so that's sort of the first thing to think about when you think about this statement, but you're going to see that it's actually more detailed and more complicated, and the details involve 2 sources of complication. First source of complication is we want to think about this constant, and we want to make it as tight as possible. Second source of complication is something that I mentioned earlier. I defined the lambda i's in terms of the Euclidean norm, the L2 norm. But you might want to define the lambda i's in terms of another norm, some other norm. And you might want to get this kind of a statement, inequalities on both sides, by some quantities that don't depend on the norm, that are independent of the norm, and to make them as tight as possible. So that's what we're going to do now. So we're going to generalize to arbitrary norms. If you remember, there's what is a norm? I think you all know, but a norm is some function on Rn that maps vectors to non-negative numbers, and it satisfies the triangle inequality, and it's multiplicative in this sense. So that's a norm. And you probably know, but maybe you don't, that norms are tightly associated with centrally symmetric convex bodies. So let me tell you about that. So given any norm, the sub-level set defined by the norm, so this is This is a essentially symmetric convex body. Essentially symmetric, closed convex. And there's a converse, if I given, conversely, given a essentially symmetric, and this also has non-empty interior. Given essentially symmetric, closed bounded convex set. With non-empty interior. Such sets are often called convex bodies. So, also known as a convex body. There's a norm associated with it, for which that formula is true. So let's call this, there's a norm, let's call this set A, convex body K. Namely, define the norm in the following way. Norm of U is 0 if you use the 0 vector. In other words, it's make sure I get this right. So, this is actually a max, but doesn't really matter. Okay, so this is an exercise to check that there's a kind of a bijection, a natural bijection between norms and essentially symmetric and convex bodies, essentially symmetric convex bodies. And so we can define the lambda i's using an arbitrary norm, and that amounts, so these lambda i's can be defined using an arbitrary norm, and that amounts to discussing points in convex bodies. So that's somehow related to Minkowski's first theorem. And so, and this is also, this bijection is also due to Minkowski. And so generalizing the definition, generalizing the previous definition for any fixed norm, we can define lambda I of L as the inf of the positive such that same definition that I had before, except now this ball is with respect to the given number. And sometimes I'm going to want to tell you exactly which norm I'm using. So if we care about the precise norm, we will write lambda norm I, or lambda ki, where k is the corresponding essentially symmetric convex body. Okay, so with those preparations, here's the theorem. um, for any lattice L, and any norm, NIN, we have these upper bounds and lower bounds. So comparing to the previous, so if you compare to this statement here, you see that I've changed the right-hand side and left-hand side. The dependence on the co-volume is the same, but I've changed the constants. And the constants involve a numerical term, which is this term and this term. And it also involves a certain volume normalization. And here, this ball is the, again, with respect to the same norm. So it's important to, so this is with respect to, the ball is with respect to the given norm. Here and here. Okay, so that's the Minkowski's second theorem. We're not going to prove it in this course. It's not terribly difficult, but it requires some care. In the next lecture, we will prove the special case of the Euclidean norm, the L2 norm. Once you have this special case, then what happens is you get this statement up to constant. So you get, this now for any fixed norm, this is a constant, that's a constant, that's a constant, and that's a constant. So it's still of interest to, once you prove it for the Euclidean norm, you still get an upper bound and lower bound on this thing for any other norm, just because any two norms are equivalent. So you get some information. But the delicate part of the proof is to really nail these constants and make them tight, and that's what was done by Minkowski, and this is the content of Minkowski's second theorem. So let's give some remarks. So so first of all, let's talk about the even in the Euclidean case, this statement that I wrote down is different from this statement by this factor. So I want to show you what happens. So in other words, the statement that we will prove is this one here. Where did it go? We're going to prove this statement here. And this statement is actually stronger than what you get from the general theorem. It's stronger both on the right-hand side and on the left-hand side. And to understand that, we need to figure out what this volume is in the Euclidean case. So for the L2 norm, there's a formula, let's for the volume of the, this is the ball in Rn. With respect to L2 the formula is a famous formula that involves gamma functions, and we don't really need the formula, but it's useful to know how this thing behaves with large n. So using Stirling's formula, you can prove this. So you can get this kind of an asymptotic. So if we think about the right-hand side of the, oops, sorry about this. If you think about the right-hand side of the inequality for the L2 norm, you get a bound roughly, so it looks like this, 2 over square root 2 pi e, quantity to the n, and n to the power n over 2. So this is some constant to the power n over 2. In this statement. In this statement here. And we're getting so some of that I've swallowed the 2 to the n inside that quantity. So that this quantity that you get here is larger than the quantity that we'll be proving, which is just 2 to the n. Okay, so we're going to be proving a statement only for the Euclidean norm, but it's a little bit stronger than what you get from the Minkowski's theorem. Another, I'll just end with 2 more remarks. So 2, the theorem is optimal. The theorem is optimal for general bodies, for general conjectures, for general norms. If you take the norm to be the sup norm and L to be the integral lattice, then you can see that the right-hand side inequality is tight. If you take the norm to be the L1 norm and the lattice to be z to the n, then the left-hand side becomes tight. So the statement is tight if you care about the generalization, if you care about the general norm. And well, there's a conjecture. So I guess let me not talk about this today. I'll talk about it next week. But there's an important question. Fix your favorite norm. And find a tight version of Minkowski's second theorem for that norm. And that, in general, that's open. And I'll state a more, so I'll just write generally open, I'll state a more precise question. It's open despite a lot of work. I'll state a more precise version of the question next week. So last thing to say, I guess there might be a question, but last thing to say before the questions is that the webpage, I'm going to put an updated version of the exercise sheet for those looking at the exercise sheets. Please, I suggest all of you to look at the exercise sheets, even if you're not getting credit for the course. And if you are looking at the exercise sheet, you'll notice that not only are there more problems added in the end, but some of the problems that were there last week are getting larger by themselves. So I'm not committed to enlarging in the obvious way by adding questions. I might make some of the questions slightly more complicated. So take a look at the questions you think you've already solved because they may have changed. Okay, any questions?
Yeah. Sorry, I missed for this last question that you wrote that's generally open. Is it known for p-norms?
I don't think it's even known for the Euclidean norms. We'll discuss it next week. I think it's basically wide open.
Cool.
So I also had a question regarding this question.
Yeah.
When you said fix your favorite norm, you want to fix a type of norm and then vary the dimension of the space, or is it about really finding the constant for a fixed norm and fixed dimension?
Both questions are reasonable. You could talk about your favorite dimension or your favorite norm, assuming you have a favorite dimension and a favorite norm. You could also talk about a kind of a family of norms with a uniform definition, like an L infinity norm or an L2 norm or an LP norm, and then think about what happens in the limit when n gets large. And in all of those regimes, there's lots and lots of open questions. Okay, so see you all next week.
תודה.
תודה רבה ברק.
בבקשה.
תודה. ברק?
כן.
אפשר להגיש את התרגילים בעברית? את התרגיל והסופים בעברית?
אפשר להגיש בעברית, אבל תראה שאתה קורא נכון את השאלות. עכשיו. אם אתה לא בטוח, הוא כבר מסדר.